So today we will discuss about the modifying factors for the endurance limit. Okay, because generally we conduct the rotating beam specimen using that method. We find out the endurance limit. So this specimen is prepared under uh, closely and carefully tested controlled conditions. The endurance strength of a component is different from the endurance strength of a rotating beam specimen due to number of factors. So these differences arises due to the fact that there are the standard specimens and working conditions for the rotating beam method. Different modifying factors used in practice to account for these conditions is this one. Here the relation between sigma E. Sigma E is nothing but endurance strength of the standard specimen, and sigma E1 is the endurance strength of the any component. So here I have written this equation, sigma E1 equal to sigma E star into ABCD. So already we discussed the standard specimen. So standard specimen has the length of 875 mm and nominal diameter of 7.657, and this specimen is subjected to the reversal bending moment. This is, and one more condition is this is highly polished. Highly polished. So this is regarding the uh, the first slide. Then we move to second slide. Here I have shown in the previous slide A, B, C, D, E. So A is nothing but your load factor. Load factor is nothing but it's a correction factor for the type of loading other than reversal bending. Already in the rotating beam fatigue testing mission, we undergone the specimen only reversal bending. In case if your component subjected to other than bending, then how to consider these modifying factors? So generally A is equal to 1 for reversal bending load, and for reversed axial load we take 0.85. This is for ferrous materials like steel, and non-ferrous materials like cast iron and other things we take 0.7 to 1.0. And for torsional loads, we take 0.5 to 0.6. In between, we take any one value. Then the next factor is the size factor. So size factor is nothing but here standard specimen used in the rotating beam machine has a diameter of 7.5 mm. For different diameters, how I consider the modifying factor? So in case the diameter is less than or equal to 7.6 or 7.5, we take B is equal to 1. In case the diameter is in between 7.6 less than or equal to D less than or equal to 50 mm, then we take 0.85. So in case the diameter is more than 50 mm, then we take 0.75. So these values have been evaluated using experimental conditions. So here, not only this, we have one more equation. Using that equation, B is equal to D by 7.62 e power minus 0.1133. So using this equation also, we can find out the B value if you know the diameter. Okay. So generally, sometimes in problems or design procedures, they don't give the diameter. So that's why you assume that the diameter is between 7.6 and 50 mm. Now, here, how to estimate the size factor? So, the endurance limit of the component is found to decrease with increasing the size of the specimen. Because if the size of the specimen increases, okay, automatically we have the more internal defects. The component have the more internal defects. So because of this, the failure may be happened due to this. Okay. Then next factor is the surface finish factor. Surface finish factor is highly polished surface finish we are using in the rotating beam specimen. But in actual practice or in any mechanical component, the surface do not have such highly quality finish. So the endurance limit found experimentally should be modified. The modifying factors depends on the quality of the finish and the ultimate strength of the material. So here formula to calculate the surface finish factor is C is equal to A into sigma ultimate power B. Here A and B are the constants that depends on the surface finish, means whether it is ground finish or hot rolled or machined cold run, like that. And the other one is the ultimate value. Based on the ultimate value, we choose the C value. Okay, so in case I have some 1.58 factor and ultimate value is this and the ground is like this, then we choose A and B values as like this. Then other factors are not that much important, but we'll discuss. Temperature factor is shown with D. So you know already any equipment operates under some room temperature or higher temperatures. If the operating temperature are below the room temperature, then a brittle fracture is the possibility of failure. And this brittle failure should be investigated first. If the operating temperature is higher than the room temperature, that is 27 degrees or 30 degrees centigrade, then yielding should be the possibility of failure. And yielding failure you require to investigate first, because the yield strength drops rapidly with the temperature. So this factor must be considered for calculating the endurance limit. It may be true that there is no fatigue or endurance limit for materials operating at higher temperatures. Generally, it varies between 1.02 to 0.567. The last factor is that is miscellaneous factor that is shown with E, and in this miscellaneous effects we consider the residual stresses, either improve the endurance limit or decrease the affects the endurance limit. Similarly, corrosion will be decreases the endurance limit. So these are the modifying factors we need to consider when designing any component. Next one is fatigue stress concentration factor. In the previous classes we seen stress concentration or previous videos. Now we see fatigue stress concentration. When a machine member subjected to cyclic or fatigue loading, so the value of fatigue stress concentration factor, that is KFT, shall be applied instead of theoretical stress concentration factor. Since the determination of fatigue stress concentration factor is not an easy task, means it takes a lot of time. So that's why a lot of costly involved. So therefore, from the experimental test, it is defined as fatigue stress concentration factor KF is equal to endurance limit without stress concentration and endurance limit with stress concentration. It is a ratio of without stress concentration to the with stress concentration. Then, so the other way, as per my notebook, I am defining the same definition, but fatigue stress concentration is important in the case of fatigue loading of machine parts. Due to the presence of stress concentration, the fatigue resistance of the part is lowered. Okay, so formula is same, notch free specimen to the notched specimen. So here we know we need to establish the relation between the fatigue stress concentration and theoretical stress concentration. So in case Kf is equal to 1 plus Q into Kt minus 1, this is for tensile or bending stress. In case you want to define the same equation for shear stress, then Kf is equal to 1 plus q into kts minus 1. Just you require to add only s because it is shear. Then, so in that equation, we seen one term q, that is kf equal to uh, in this kf equal to 1 plus q into kt minus 1. Here q is nothing but the notch sensitivity. So notch sensitivity is due to the presence of irregularities. Notch means it is the due to presence of irregularities, where q is the notch sensitivity for fatigue loading. The value q varies from 0.0 to 0.70. This index value is smaller for ductile materials, but it increases as the ductility is decreased, as done by the heat treatment. The value of heat treatment may be calculated by using this equation, Q equal to 1 by 1 plus A by R, where R is the notch root radius and A is the material constant. So this is the formula. From this Q is equal to, just I write Kf, take this minus 1 divided by this Kt minus 1. Just from that equation we get this equation. So these are the references I used for preparing this PPT. Thank you.